Hi, kids. My name is Kevin. I'm a member of the SHARP Lab, and I study the effects of mutations on evolution. And I'm here with my colleague, Catherine, who works in the Wellick Lab. We'll talk a little bit about that in a second. But we're here today talking about mutations. Now, for the first question you guys probably have on your mind is, what are mutations? Mutations are changes in the letter code of your DNA, the molecule that makes up your genetics and determines a large number of your traits and how they will come out. Mutations are changes to those things and they cause differences between individuals. For example, you may have blonde hair, whereas a friend of yours might have black or brown hair. Some people might be shorter and others might be taller. And these are all examples of the genetic variation that comes from mutations. Mutations additionally also create differences between individuals in terms of their fitness and their survival. Um, and we'll get to that in a second. But in our lab, we study mutations that manifest themselves in easy to study ways. The first picture you see here is an image of a normal fruit fly. It has a standard red eye, dark body, and wings, right? Obviously, they call it a fly for a reason. But you can see here in this first mutant we have, it has no wings at all. And this is caused by a change in a gene that controls wing development. Similarly, a change in the eye color gene causes this fly to end up with completely white eyes. But these are the sort of things that are pretty similar to people. We also have people who maybe have, longer or shorter legs, or perhaps have different colored eyes. So, what about things that we can study in terms of fitness? Well, for this, we use a tiny microorganism called yeast, and we study the growth rate of yeast. Here we have a graph showing how fast the yeast is growing over time. And you can see that the strains, which have different mutations from other strains, this particular red strain of yeast is growing a lot faster than everybody else. This creates a real difference because if you have a population of red and normal yeast, because the red yeast grows faster, eventually the population will be made up of more and more red yeast. And this is the effects of a process we know as natural selection, by which organisms who are more fit or better suited for the environment are able to produce more copies of themselves. But natural selection also acts in the opposite way. If we go back to the previous graph, I have now outlined certain strains in blue. These blue strains tend to grow much more slowly than the other strains. And thus they have negative or deleterious mutations. And so selection would act against these deleterious mutations. This creates a dynamic in which good mutations are reinforced by selection and deleterious mutations are selected against, creating a force that moves an organism along its fitness landscape. If we think of the peaks as the points at which you are most fit, an organism would want to move towards a peak. But sometimes, if you're starting out in a valley or if you're starting out somewhere else, mutations can either increase or decrease your fitness accordingly. And so, thus, mutation acts as an important resource on which selection can act in order to produce new variants and to increase the fitness of individuals. However, that's not the complete picture because most organisms have had millions of years to adapt to their environments. So, thus, in reality, most organisms sit atop a peak, and the vast majority of mutations, rather than being positive, actually end up being negative.
Hello, everyone. As Kevin said, my name's Catherine, and I'm in the Wellick lab. And so our lab studies how mutations cause problems in organisms. And so I work with mice, and we study a particular mutation that causes bone defects in those mice. And so to continue what Kevin was saying, natural selection is this process that should select against mutations that cause disease. However, modern medicine has allowed conditions to defy Darwin's laws. In fact, current estimates state that 10% of the world's population lives with a genetic disease, which is about 7.6 million people. Of that 10%, 300 million people live with a rare genetic condition. I'm one of those 300 million people who has a mutation that causes a disease and is rare. Mendelian diseases are those that are inherited through specific patterns, which means we can predict the inheritance of certain diseases through these patterns and trace them through family histories. If we look at this chart here, penetrance on the y-axis is the proportion of individuals carrying a particular gene that expresses a trait. Allele frequency on the x-axis is how common an allele or gene variant is in a population. Allele frequency can be a variant that causes mutations that are associated with diseases. And so if we look at this top blue circle on the graph, Mendelian diseases that are highly penetrant and those that have very rare allele frequencies are the diseases that should be selected against. However, as I mentioned before, there are millions of people living with these rare conditions who defy Darwin and continue to live. It should be of note that people with these rare conditions face a unique set of obstacles. The most challenging obstacle that people with rare conditions go through is what's called the diagnostic odyssey. And basically, it's this patient's journey in order to get a diagnosis for their condition. You see, patients who have rare diseases, time is very important to them because their disease can increase and get worse with time. And so it's a very precious resource. But this diagnostic odyssey takes patients through lots of loops and turns trying to get an answer to their problems. This could be due to the fact that access to healthcare is not equal or that quality of healthcare is not equitable. Additionally, rare diseases specifically are undertaught in medical schools and understudied. This leads to a lack of knowledge holistically in the medical community, and which means doctors are not as well aware of how to diagnose and spot these diseases quickly. However, we can use shared databases and diagnostic sequencing to connect patients around the world. I'm one of the lucky patients who has had my DNA sequenced. And so my rare mutation shows up on GeneNatcher, which means if somebody else on the world has my mutation, we'll be matched and scientists will be able to study us to hopefully find treatments and cures and make research go faster to better help individuals living with these diseases. It's important to know that individuals with rare diseases or any disease-causing mutation can still live full lives. However, improved medical treatments will enable them to live easier ones.